Okay, today we're going to talk about really the RMP, or the resting membrane potential of a cell membrane, and how it is established. We'll kind of talk about different things with kind of what characteristics of the cell membrane account for the resting membrane, membrane potential's development, and things that can change the magnitude or the size of our resting membrane potential. So I'll just do part one right here. So it's important to remember that with the cell membrane, we have a phospholipid bilayer, which means we have these phosphate heads with these fatty acid tails, these lipid tails. And what these do, what this layer does, is it creates a kind of a selective permeability barrier. With the heads here on the outside of the membrane, this is hydrophilic. So things that are like water would be able to interact with this here. On the inside is hydrophobic. It's kind of like with oil, fat. Doesn't really like to mix with things that are like water or even ions. So ions have a hard time crossing through this barrier. And this is what our whole cell is made up of with that layer. I'm just going to kind of go like this, just kind of show that. So it makes it really hard for things to cross that barrier because of this phospholipid bilayer. So this creates a need for pretty much proteins that allow kind of some openings. We call them channels into the cell, so things can move in and things can move out. Awesome. Two ions that we're going to be talking about a lot will be potassium and sodium. These are huge with membrane potential, action potential, and just kind of how cells really function. The cell is able to create a gradient of these things and make it do stuff for us. One important pump that we always talk about is the sodium potassium ATPase pump, which pumps out 3 sodium ions and then brings in 2 potassium ions. And this requires energy, ATP. Eventually, this creates a huge gradient where there's a ton of sodium on the outside of the cell, and there's just a ton of potassium inside the cell. So it makes it have a drive that potassium would naturally want to leave the cell, right? And then sodium would naturally want to come in. With these channels that the cell has, it can kind of manipulate those concentration gradients to make it do stuff, certain things it wants to do. For example, with potassium, it's wanting to leave the cell because there's so much in here and so little out here, right? All around the cell, there's a ton of sodium or potassium leak channels right here that allow potassium to leave. As the potassium leaves, it's going to want to go from the high to low, right? But there are also a lot of negative charges along, the membrane, and also positive on the outside. As the potassium is leaving the cell, it's leaving a lot more of these negative charges behind. As more of the potassium leaves, these negative charges will be like, well, we need some more positive in here. We're losing too much positive. So it'll actually kind of start to pull back a little bit and resist that chemical gradient with an electrical gradient. So it'll reach a point of equilibrium where there's still quite a bit more of potassium inside the cell than there is on the outside with this electrochemical gradient. This creates basically a resting membrane potential, and it typically sits around like -70 right here, because there's just a buildup of these negatives here inside the cell, and the potassium's trying to leave there, so it's leaving it a bit more negative. Let's see. Perfect. Yeah. So that reaches the point of equilibrium, and the net movement is pretty much 0 of potassium leaving here. Sodium doesn't really do too much to make that resting membrane potential more positive because it lacks kind of channels that go into there. It does have voltage gated channels, so it depends on a certain voltage, which we call threshold, which is a point where those sodium gated channels open. But unless we get up there, they're not really doing too much, and sodium's not able to really permeate through the cell membrane. Things that can affect this, I guess, resting membrane potential, which we would just represent with RMP, is pretty much the amount of the concentration and the extracellular kind of environment of the cell. So like we have, for example, hyperkalemia. Hyperkalemia is basically, if we break it up, so hyper just means a lot, and then cal means like potassium, and then emia or lemia means blood. So there's a lot of potassium in the blood, or just like outside the cell. So we have this gradient, right? There's a ton of potassium on the outside of the cell. It's only driven really to move outside the cell because of that chemical gradient of less potassium outside the cell. But if we increase that with hyperkalemia, there's less of a drive for this potassium to leave the cell. It'll still want to leave the cell because there's still just a ton inside the cell. But if there's already quite a bit on the outside, it'll be less inclined to leave the cell. So what this will do is it will make the resting membrane potential become a bit more positive. So let's just say it was like -60. Brings it closer to this threshold that we need to hit an action potential, which we can talk about more later. Because it's more positive inside the cell because we have more of the potassium ions staying in there than are leaving behind the negative ions right here. Let's do a different color. With hypokalemia, same idea, except right here, hypo means less. With hypokalemia, it means that there's less potassium in the blood. So even less out here. So already we know that there's just a ton of potassium inside the cell due to the gradient that was created with the ATP pump, sodium potassium pump. So before there's already quite a bit less in comparison to the inside of the cell potassium on the outside. But now with hypokalemia, there's even less. There's like even smaller. I can even draw how small they are. So now it's like, holy cow, there's way less out here. We need to get out there and create equilibrium, make things even. So we'll leave outside the cell, resist that electrical gradient, and leave behind even more of the negatives inside the cell, which would make the resting cell membrane potential become even lower. So let's just say it was -80 here. Cool. So these are some things that can affect the resting membrane potential. And then we talked about different things that could affect or go into making the resting membrane potential. There's also the Nernst equation and driving force. This helps us to know like why sodium wants to leave the cell, or sodium wants to enter the cell, and why potassium wants to leave the cell. So we have the different equations. So we have the Nernst equation, which is represented by, so E equals, it looks similar if you've ever taken Chem 106 here at BYUI. It's just a general chem unit on electrochemistry. But you have, so this is just pretty much a value. It's accounting for temperature, pressure, stuff like that. And then this right here, the Z, is just the charge of your ion. So if you had something like calcium, which has a +2 charge, it would be a 2 there for the Z. Or if you have potassium, it'd just be a +1, so there'd be a 1 up here. And then you have the concentrations of the inside of the cell compared to the outside of the cell. So let's just, for example, say we had a cell right here with a concentration of potassium of like 150 millimoles. And then on the outside we have 5 millimoles. So there's a lot more concentration on the inside of the cell. So now we can kind of predict like where the cell, like where the potassium will go. So we can plug it into the Nernst equation. So here's 61.5 over Z, since it's potassium right here is a +1, so it'll just be 1. We take the log of the concentration of the inside of the cell, which is the 150, divided by the 5, which is on the outside. And this should give us a -91. Cool. So this is talking about mainly, it's like the potential of this thing right here. It's going to want to leave the cell. But this is the only problem. The problem with the Nernst equation is that it assumes that like potassium is the only ion that's going to be crossing through. It's going to be influenced by anything else, which is not true with living organisms. We have a lot of different ions happening. So that's where we bring in the equation of driving force. So I'll just represent it with dF. And that equals the voltage of the membrane, so it could be at any point, minus whatever we get for this value for the Nernst equation. So minus E. Okay. So let's just say we had a membrane with a membrane potential of, let's just say like 30. So I like a +30. So inside the cell, this is always talking about inside the cell. And then we have this here for potassium, so -91. This would give us a +121 on the inside of the cell. So this would be the driving force for potassium. It's kind of like the drive it has to move a certain way. Since potassium is positive, and the inside of the cell is going to be positive, potassium is going to want to leave the cell, leave that positive charge, because the positive charges pretty much repel each other, right? So it's going to want to leave. And with this number being pretty large, it's going to have a huge drive to leave. It's like, get me out of here. Get me out of here. I got to go outside of the cell. If it was something like +30 or +5, it's going to have much less of a drive, but nonetheless, it'll still want to leave the cell. So this is more on the resting membrane potential and kind of how it's established with the membrane that we have and factors that can affect it, as well as the Nernst equation and driving force equation and how it's applicable to this. Okay, in this part 2 of this essay, we're going to be talking about the action potential and different components of it. So to start off, we're going to start with the graph. We already talked about the resting membrane potential, which is where potassium's leaving the cell with an electrochemical gradient. And at equilibrium, it leaves the inside of the cell being around -70 millivolts. Right here. I'm going to draw a quick picture of it, of what an action potential looks like. Pretty much like that. We're going to talk about each of the different kind of parts of it. So I'm going to label it here. So we have one. I'm going to draw this actually. Okay. 1, 2, 3, 4, 5, 6, 7, 8, and then back to 1. Okay. So we already talked about the resting membrane potential, how it's formed, and kind of like why it's a negative number, right? Awesome. So at this one point, we're just going to go like this. 5, 6, 7, 8. So at 1, there's just the potassium leak channel that's going on. That's what's creating this -70 millivolts voltage within the cell. So we just have our potassium leak at 1. But at 2, at some point, some ligand and mechanoreceptors start opening, right? And they start allowing a positive charge into the cell. It could be like sodium, bit of sodium. It could be a bit of calcium coming in, or it could be chloride leaving, which is negative, so it would make the whole cell more positive. It do that and make the pretty much just start to go up here. We call this a depolarization. As we're going up, this is a depolarization. Okay. And it'll go up, so we'll just say some ligand or mechanoreceptors are starting to let ions move, and it's making the whole thing more positive within the cell. Receptor. Okay, cool. At 3, we reach something called the threshold. This is right where you need to get to have an action potential, have something occur within the cell. It typically occurs around like -50 or -55 millivolts. And to talk about what's happening there is, so we have a sodium-potassium voltage-gated channel right here. Let's go like this. So this is typically what it looks like. So you have this kind of like this little spring thing right here. It's called an alpha helix. So this is our sodium-potassium voltage-gated channel. This alpha helix is full of calcium. So it has like Ca2+, right? Okay. So what happens is that within the cell, we have, becomes more negative. Yeah. Okay. So with the cell, on the outside of the cell, normally it's more positive, and then we have it more negative on the inside here, right? What's happening is that these positive charges on the outside of the membrane are actually pushing down on this calcium, because positives repel positives, right? And these negatives are pulling down on the alpha helix. And what this alpha helix is doing is it's connected to this gate, this activation gate, and it's keeping it shut. These repulsions and attractions of these charges are affecting the calcium, which is affecting this gate and keeping it shut. So no sodium can ever enter into the cell if it's shut, right? Well, because in step 2, some ligand or mechanoreceptors are allowing movement of different ions to make the cell more positive. It ends up going down to a phase kind of like this. I'll just go. Ends up doing this. So you get your receptor right here. And then you get this. So it starts to get more positive on the inside of the cell. So you get more positives with those negatives, and then on the outside you're kind of getting rid of some of those positives, right? Because they went into the cell, kind of more negative. And what happens is that it starts to do the opposite, right? These positives start to kind of push up on that, and the negative out here starts to kind of attract it, right? And it allows that gate to start opening up a little bit right here. But since we know that sodium has a huge kind of driving force to come into the cell, because there's so much more of sodium on the outside than there is on the inside, it's going to want to come in. So once that starts to open, it'll start to flow into the cell. And this occurs at threshold when that gate starts to open. So we can say right here at 3, there's kind of always a potassium leak channel going. So I'm just going to do this. It's pretty much always going. But then we have, in addition, our voltage-gated sodium channel. And then we also have a voltage kind of potassium slow opening. That starts to kind of open as well, but it's not really having much of an effect at this point. So when all that sodium comes in, it starts to shoots up here, and allows a lot of sodium to come to the cell. Sodium's positive, so it's going to make the whole cell a lot more positive. It keeps doing that, even to 4. So you have your leak here, and then you have your sodium, potassium, or sorry, your voltage gated potassium or sodium, and then you also have this potassium one, slow. Okay, so it's going up, it's depolarizing, going up, and it reaches a point right here at kind of negative 55. So it's staying open, but it only stays open for a short time because the conformation of the proteins here with these things here, they're kind of set like on a bit of a timer, especially this when you're in activation gate. And what happens is that when this opens after a certain amount of time, this inactivation gate will actually swing in, shoot, and close off that gate, even if this is open here. And it'll stop the flow of potassium from coming into the cell. So now we're at 0.5. So our voltage gate stops for sodium. We just have our leak, and then we have our potassium pump open right here, the voltage gated one. Since potassium is wanting to leave the cell, it's positive and it's leaving a bunch of negatives behind. It's going to drastically drop our action potential right here. Shoom, a lot down. And since this is open, there's a lot more that's going to be coming into the cell. And this is called this is repolarization, when you come back down, kind of become more negative. And sorry, something to mention here is you have your absolute refractory period. This is where you can't have another action potential occur. This is due to the fact that you already have sodium coming in, right? Once this is open, like there's nothing else you can like really do to have like another action potential, because it's like it's already happening. This thing's open, and really you can't do much to like anything more to get it to have another action potential, if that makes any sense. Perfect. So then anyways, yeah, so there's nothing you can do there. And then anyways, this leak channel is still going. This voltage gated potassium is open as well. A ton of potassium's leaving, dropping us down, and then it reaches this point, this 8 point, and it goes even past what it was before for the cell, at negative 70 at resting membrane potential, because there's just so much more potassium that's able to leave because of all the channels and stuff. This is called hyperpolarization. Polarization, when you just go too far, it's too much. But eventually with our sodium leak channels, and then with this one shutting, at step 8, we'll just have our sodium leak, or potassium leak, and it'll reach back to equilibrium and go back to this resting membrane potential, where everything's happy at equilibrium. Everything's kind of at a state of balance, no net movement, really. During this time, you could technically have another action potential occur, but it's really hard because you're a lot more negative at this point at 8 with the hyperpolarized state. But it's technically possible, so they call it the relative. It's relatively refractory. And since it's more negative, you technically could have just kind of a larger stimulus, and you would just need a lot stronger of a stimulus to make these things open, because it would require more effort to go from the 8, which is a lot more negative, to get to the threshold at the positive negative 55 than it would at normal resting membrane potential. But this is pretty much what's happening here. So you had your kind of brief overview. From 1 to 2, So 1 is just your potassium leak channel that's going, it's at equilibrium. But then at 2, some ligand mechanoreceptors start opening and the cell becomes more positive. So that could be, a little bit of sodium entering in, it could be calcium entering in, or it could be chloride leaving, whatever it may be. At 3, you reach threshold, which is where your potassium leak channel is open because the alpha helix that's keeping it shut, the activation gate here, will allow it to open. And a bunch of sodium will rush in, make the cell a lot more positive, reach up to 5. Our inactivation gate will swing in and shut it. So then we'll just have our potassium leak channels and our voltage gated potassium channels that are allowing the potassium to leave and making the cell more negative. So it'll drop even to hyperpolarization, but then it'll just be our potassium leak channels that will bring it back to equilibrium, and it will be able to do another action potential later on, just like that. This is part 2 of our essay. Okay, now we're going to talk about a graded potential and kind of how it differs from an action potential. So previously we were talking about the action potential, which is where the inside of the cell is able to get positive enough by the opening of different channels, mechanoreceptors, ligand receptors, and the inside of the cells get positive enough so that it reaches threshold. So then all of our potassium voltage gated channels are able to open up and fire and send a signal. So this is with an action potential, which you see going across the neuron here. What we have with a graded potential, oops, I want to erase the whole thing. Here with the graded potential, we have kind of our synaptic cleft, where we have our presynaptic terminal and then our postsynaptic terminals right here. 2 different neurons. One's an inhibitory neurotransmitter, and then we also have an excitatory kind of neuron. So what we have on the end of this channel here is different kind of channels on the end of this neuron. We have a chloride channel, calcium, and also a sodium. What we're trying to do is we're trying to get the inside of the cell positive enough so that we can send that action potential or send that signal. So what we have is inside of these postsynaptic terminals right here, we have different vesicles with different neurotransmitters, which are basically chemicals. So we can have an inhibitory neurotransmitter in this inhibitory neuron, and that's going to make it harder to send a signal. And then we also have over here the glutamate, which is an excitatory neurotransmitter. So what these do is that they, for example, right here with the glutamate, it will attach to the site, this kind of ligand, this kind of receptor, and it'll allow it to open up and let all these kind of ions that are floating around. We have calcium, chloride, sodium, right? So there's different channels for specific things. And for example, for this calcium, once that has that that neurotransmitter that connects to it, binds to it, door opens up, and calcium is able to rush into the cell and make it more positive. And the same thing happens with the chlorine that goes in. It can make the cell more negative. So with our graded potential, we have something called spatial summation. With spatial summation is where we might have multiple of these sodium or calcium channels kind of all around this opening that are being opened. Because normally if you just have like one, it'll go up when that sodium comes in, but then it might not have enough to get to the top and open up all these sodium voltage gated channels. So kind of just drop back down here. But with spatial summation, we have multiple that are starting to open up, and it starts going like, okay, more open up, it's becoming more positive, and then it opens up. opens up our, or hits threshold, and it sends that signal because all these sodium potassium channels are starting to open up. We also have temporal summation, which is over time a channel allows the cell to hit threshold. So if we have just like the one sodium channel, it's pretty much just like, let's see, like this. So it starts opening up, starting to get more positive on the inside, more positive along this membrane on the inside, intracellular membrane. And it'll start to go up, we'll kind of level out, and then with time, more will start to come in, go up, and then eventually it'll hit threshold and send that action potential. So these are what these graded potentials do, is they help us to get to that threshold to send off that action potential there. We have the inhibitory thing that can make it harder to send the signal, or we have the excitatory, which is going to make it easier to send it because it's making this inside of the cell more positive, allowing these voltage-gated channels, which open up at the negative 55 threshold. So it's coming more positive from the standard kind of equilibrium of negative 70, just based on the potassium gradient. But this is more dealing with graded potential and how it compares with the action potential. Okay, now we're going to talk about capacitance. Capacitance is represented by this equation right here. C represents capacitance, and then Q is pretty much the number of charges, such as like plus and minus, right? And divided by the overall voltage of the cell or cell membrane. So we have a first example right here on the top, something of high capacitance. So we have a thin neuron right here, something thin, and the outside of the membrane is positive. So we have a lot of positives here on the outside, and then we have the negatives on the inside. They're able to have a stronger kind of connection here, which is represented with the red here. Since they're a lot closer, they have a stronger interaction. A lot more energy is spent trying to get closer right here. They're already close, so they're trying to maintain that. But since they're spending kind of that energy, I guess you can think of it, they're not able to really push as hard on new other charges. So you can pack a lot more of them in closer together because they don't have that energy to repel each other away because they're already pretty much going into the other opposite charge. So this leads to a high capacitance because we're able to fit a lot of charges for a set voltage of negative 70 within the cell. Right here on the bottom is an example of the low capacitance. So this is a myelinated sheath right here. Myelin creates a further distance between the positive and the negative ions. And since there is that stronger distance, they're not spending as much energy trying to go to their opposite charge here. So they have more energy to repel their other charges here, just like this, right? So you can fit less of them in a certain area. But still they maintain a negative 70 millivolts of charge. So now we have less of our number of charges, but the same voltage in between the two. So this one's going to have a lower capacitance because you're dividing a smaller number from the same number, if that makes sense. So that's dealing with capacitance. And then we also have here what do you call it? It's called the length constant right here, length constant. And this equation is kind of like this wave thing right here. That's what it represents. This is membrane resistance right here and internal resistance. Okay. It's easiest seen when you're looking at a myelinated neuron. So right here, pretty much membrane resistance is the membrane being able to resist things from crossing it, right? So if you have like a normal neuron, you got a ton of channels, right? Just kind of going all along, allowing things through. But in comparison with the myelinated sheath, this myelin right here prevents there from being any channels right there. So it prevents really any, I guess, neurons from, or channels from taking up that area. So it lets less things cross the membrane. So this has a higher membrane resistance than something like this. This would have a lower membrane resistance right here. Okay. Internal resistance is more dealing with the different charges, negative charges, things that are kind of like blocking the way of our length constant, which is basically this gluon, this pretty much sphere of this influence thing that goes down a neuron to be able to send different signals. Because you get these positive charges that come in from like these channels on the outside right here from like your sodium, for example, that go down and are making it gradually more positive or positive to send these action potentials all along the neuron. But things can get in the way of that and cause some internal resistance within the neuron or the cell, I guess. And that can be negatively charged proteins that will that positive charge is too busy trying to kind of neutralize that charge that it doesn't make it as far there. So with the cell that has less of these, less kind of membrane resistance within it, but with a high membrane resistance, has a further or bigger length constant or larger sphere of influence a lot across the neuron. This is why that myelinated sheaths are generally better, or have length constants that are kind of send signals a lot faster, is because that sphere of influence for every channel that's able to have a stronger effect on the whole neuron, making it more positive than something like a normal neuron with a lower membrane resistance, and it still has those kind of internal resistance within the membrane. But this is talking more about capacitance as well as kind of how capacitance and length constant are affected by myelin. Myelin give you a lower capacitance but a higher length constant.